Hello, welcome back. The purpose of this web lecture is to give you a very brief overview of the general chemistry principles that you'll need to understand the biological mechanisms we're going to be dealing with this semester. So hopefully for many of you this will be a review of your high school biology class, but for those of you who maybe didn't take chemistry in high school, this should give you just enough chemistry to get you through the next few sections. As I mentioned on the first day of class, this course is going to be about biological mechanisms. What makes these biological processes go? What makes them work? How does biological organization arise? And as you go through this semester, you'll hear a lot of vague sounding explanations such as molecule X moves along its concentration gradient. Ion X is attracted to its opposite charge. Molecule X has a natural affinity for molecule Y. Molecule X binds reversibly to its receptor. All of this kind of sounds like there's some kind of intention or desire among the molecules to do these things, and it sounds very, very mysterious. But what do these things really mean? Do we really think that molecule X is just, for some reason, likes the look of molecule Y and wants to get closer to it? We're going to look at why these things happen. So we're going to answer most but not all of these questions in this web lecture. We'll deal with diffusion along concentration gradients when we get to cell membrane function. But let's take a look at what these things really mean. And the one thing I really want to emphasize is that biology really is just chemistry and physics working under some special circumstances. So biological processes can be incredibly complicated. Think back of that developmental sequence I showed you on the first day of class of the frog development, all of these cells arranging themselves. It can look really mysterious. It can be very, very complicated, but there was really nothing magical about them. It's basically a lot of really complicated molecules doing what those molecules do naturally in the non-living world. So even the most complicated processes can be understood using the same laws of chemistry and physics that rule the non-living world, with some special conditions, as we'll see as we go through the semester. So the first concept that the book emphasizes is that matter consists of chemical elements in pure form and in combinations called compounds. So first of all, what is matter? Organisms are composed of matter. What do we mean when we say matter? Matter is anything that takes up space and has mass. So no matter how little space that is and how little mass that is, if it takes up space and has mass, this is what we call matter. And matter is made up of elements. So atomic theory tells us that all matter is composed of atoms, these tiny little submicroscopic particles that come together to create matter, and atoms can be categorized into different kinds of elements. An element is a substance that cannot be broken down to any other substances by chemical reactions. The compound is a substance consisting of two or more elements in a fixed ratio. So there are different kinds of compounds that we will examine as we go along in this web lecture. The important thing to know now at this point about compounds is that they have characteristics, they have properties that are going to differ significantly from those of the individual elements that make up that compound. So as an example, I think this was the example in your book, if you take sodium, which is a metal, it's highly explosive, so it combines readily with the moisture in the air with water and basically bursts into flames. So this is a very difficult element to work with in its pure form. And you take that and you combine it with a poison gas, basically. So chlorine is a component of some chemical weapons. It's highly toxic. But you put them together and you get something that is very tasty on French fries. Sodium chloride, regular table salt. So that's an example of how when you put the two elements together and combine them into a compound, they can have very, very different properties. So what determines the properties of an element? The properties of an element are determined by the structure of its atoms. So let's take a look at how atoms are put together. Atoms are composed of subatomic particles. There are lots of different kinds, as we know now, but the ones that we're going to be dealing with in this discussion are neutrons, which have mass but no electrical charge, protons, which have mass and a positive charge, and electrons, which are matter. They have some mass, but their mass is negligible, and they have a negative charge. So the neutrons and the protons form the atomic nucleus. They're going to stay in a central location. Electrons form sort of a cloud of probability. You'll learn more about this when you take chemistry, but the cloud is determined by the probability of finding an electron in a particular spot at a particular point in time. So they form this sort of cloud of negative charge that encircles the nucleus. The neutron mass and the proton mass are almost identical to each other and are measured in Daltons. So for the purposes of this course, we're not going to worry that much about atomic mass. You're going to deal with it a lot in chemistry, but just know that in general, the mass of the atom is determined by the masses of all of its neutrons and protons. So to look at this in a more visual way, you can think of this would be a helium atom with 2 protons and 2 electrons. You can think of this nucleus with this cloud around it. I talked about the probability of finding an electron. The darker color represents a greater probability of finding the electron there, and the lighter color represents a lower probability. Or you can think of it just in terms of these electrical charges kind of orbiting around this positively charged nucleus. So electrons have energy associated with them, and they can have differing amounts of energy. So what do we mean when we say energy? Energy is the capacity to cause change. So we know about kinetic energy. You've probably heard of potential energy due to height. So a ball sitting on top of a hill has potential energy due to its height above the ground. And so if you push that ball off the edge of the hill, it's going to convert that potential energy into kinetic energy. So the potential energy is its energy due to position. But there are also other kinds of potential energy, and in general, potential energy is the energy that matter has because of its location or structure. So there can be potential energy associated with chemical bonds. There can be potential energy associated with a spring. If you compress a spring, it now contains potential energy. When you let it go, it can be converted into kinetic energy. So there are different kinds of potential energy. So think of this as just the capacity for movement at some future point when conditions change because of its location or structure. The electrons of an atom differ in their amounts of potential energy. And an electron's state of potential energy is called its energy level. And we can think of this as a series of electron shells at different distances from the nucleus. So remember that electrons are attracted to positive charges because they're negatively charged. Opposite charges attract one another. So their lowest energy state is being very close to the nucleus. When we conceptualize these shells, we say that an electron can be in only one shell at a time, and it can never be between shells. So one way of thinking about this is think about a ball rolling down a set of stairs. It can come to rest on a step, but it can't ever come to rest between steps. It's going to be on this level, or it's going to be on this level, or it's going to be on this level, or it's going to be on the floor. Same thing with electron shells. It can be in this closest shell, it can be in the next shell out, or it can be in an even farther shell. So lower energy states are the most stable. So if we think about this as simple potential energy due to height above the ground, we can say that whenever it has some potential energy, there's some capacity for change, and it's not going to be stable, right? It's just going to take a little shove to get it rolling down to the next step. But once it's all the way at the bottom, it has no potential energy, and it's going to be stable. It can't fall any further than that. As I mentioned before, electrons are attracted to protons but repelled by each other. So the lowest energy state for electrons is to be as close as possible to the nucleus without getting too close to other electrons. This is going to be the most stable state. Because of this, electrons are going to tend to occupy the shell closest to the nucleus first, but only 2 electrons can occupy that nearest shell before the electrons start to repel each other and become too close together, causing a higher energy state or a less stable state. So in this innermost shell, we only ever find either 1 or 2 electrons in this nearest electron shell. And so if we start to look at the individual elements, the first 2 on the periodic table are hydrogen and helium. Both of these just have this 1 electron shell. Hydrogen has 1 electron in its single shell. Helium has 2 electrons in its single shell. And we refer to these electrons that are occupying the outermost shell for that element. So in this case, it only has 1 shell. We call those electrons valence electrons. Those are the ones that are in the outermost shell, or we also call this the valence shell. And the chemical behavior of an atom is mostly determined by the valence electrons. Elements with a full valence shell are chemically inert, such as this helium that has its maximum number of 2 electrons in its valence shell. So now if we go to the next row of the periodic table, we have elements that have 2 electron shells. So again, there's this innermost shell, which is always full in these because electrons are going to occupy this shell first. So you'll notice in these diagrams, this inner shell always has 2 electrons in it all the way across. The second shell and all of the outer shells have 4 orbitals. And each orbital can hold 2 electrons. So the innermost shell, the first shell, has only 1 orbital. The rest of these have 4. And this is represented by sort of the 4 corners of the circle on this. Because electrons repel each other, there's going to be 1 electron in each orbital before they'll start to pair up within an orbital, right? They don't want to have 2 electrons in the same orbital because they're going to repel each other. So they're going to get as far away from each other as possible. So in lithium, there's only 1 electron, and it's going to occupy 1 orbital. Beryllium is going to have 2 electrons, and they're going to occupy 2 separate orbitals. Boron with 3 electrons, 3 separate orbitals. And then carbon now has 1 electron in each of those orbitals. Now they'll start to pair up in nitrogen with its 5 electrons in the valence shell. So now you have 1 pair of electrons and 3 unpaired electrons. And then they will start to fill the other orbitals as we go across to neon, which has a complete valence shell. And same thing, looking at the third shell, again, there are 4 orbitals that each hold 2 electrons, and they're going to load up in the same way. First in 1 orbital, then the next, then the next, and then once there's 1 electron in each of those 4 orbitals, then they'll start to pair up, as you see here, 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 and here. And this is how the periodic table of the elements is organized. So if you look down the rows, all the elements in each row has the same number of electron shells. It says 1 shell, 2 shells, 3 shells, 4 shells, etc. And if you go across the columns, each of these columns have the same number of valence electrons. So this one has 1, but as you go along, this one, lithium, has just 1 electron in its valence shell, 2, 3, 4, 5, 6, 7, and then finally neon has a completed valence shell with 8 electrons in the valence shell, plus the 2 in the inner shell for the atomic number of 10. So next concept, the formation and function of molecules depend on chemical bonding between atoms. Why do atoms bond together? Why do elements bond together? We're going to look at this question next. So the lowest energy state, in other words, the most stable, is for valence shells to be filled. Those outermost shells are most stable when they have a complete set of valence electrons. And this is why the elements with complete valence shells, such as neon, argon, helium, we call them the noble gases, they're unreactive, they're inert. So the number of bonds an atom will make depends on the number of unpaired electrons in that valence shell. Unpaired electrons make it unstable. So we'll start by thinking about covalent bonds. So we can think of this as two atoms that complete each other. You complete me. It's so romantic. A covalent bond is the sharing of a pair of valence electrons by 2 atoms. So if we look at this in Diagrammatic form, we've got our hydrogen atoms, one proton, an electron cloud around it with a single electron. So this is electrically balanced, a single positive charge, a single negative charge, both of these. But again, they're not stable because their valence shell is not filled. So as they happen to move closer and closer together, when they get close enough, they're both going to sense the presence of that other electron in their valence shell, and that's going to make them more stable. So now they're still neutrally charged, positive charge and a negative charge on this molecule, positive charge and a negative charge on this molecule, but now they both have a completed valence shell by sharing that pair of electrons. So in a covalent bond, the shared electrons count as part of each atom's valence shell. So now they're complete and more stable. So this is what we call a molecule. When we say a molecule, we're talking about covalently bonded atoms. Two or more atoms held together by covalent bonds, these sharing of electrons to complete the valence shells. A single covalent bond or a single bond is the sharing of one pair of valence electrons, but you can also share two pairs of valence electrons, and this is called a double bond. On rare occasions, three pairs of electrons can be shared to form a triple bond. So as an example, we see carbon has 4 unpaired electrons in its valence shell. So carbon can form either 4 single bonds, 1 double bond and 2 single bonds, or 2 double bonds, or rarely a triple bond and a single bond. And so we say that carbon has a valence of 4. It has a bonding capability of making 4 bonds in any combination of single or double bonds. Another example, if we look at oxygen, we can see that it's got 2 pairs of electrons in its valence shell and then 2 unpaired electrons. So oxygen can make 2 single bonds or 1 double bond. So we say that oxygen has a valence of 2. It can make a total of 2 bonds. And as an example, we can see carbon bonded to 2 atoms of oxygen to make carbon dioxide, and we see that carbon has its 4 bonds, a double bond with one oxygen, a double bond with the other oxygen. Each of the 2 oxygens has a double bond with carbon for its valence of 2. Here's some other examples of molecules that form where you can see the valence of the different atoms. I want you to make sure that through your reading and through watching this web lecture, you're very comfortable with the different ways of representing these molecules, either with the molecular formula, so in the case of molecular hydrogen, H2, these electron diagrams, so we can see the 2 electrons being shared by the 2 hydrogen atoms. The dot structure you'll see less often in biology, more often in chemistry, but each of these dots between the H's represent one of the 2 shared electrons. Or more commonly in biology, we represent the single bond by just a single line between the 2 hydrogens. Sometimes it's very helpful to look at these space-filling models to see the actual shape of these molecules. So here we have an oxygen molecule sharing 2 pairs of valence electrons. We can represent that as a dot diagram. Again, we're representing all of the electrons, so the paired ones and the shared ones. And then we can also represent that double bond with a double line. And you'll notice that oxygen, with its valence of 2, each of them make 2 bonds to each other. We can think about water. Water is going to have a particular shape because these pairs of electrons are going to be as far away from each other as possible, and so the pair that are shared with hydrogen are going to be kind of evenly spaced with the 2 pairs that are not shared to form this kind of bench shape. And again, oxygen with a valence of 2, bonding to 2 hydrogen atoms, and the 2 hydrogen atoms each have a valence of 1. Make sure you understand why hydrogen has a valence of 1. And down here at the bottom we have an example of a carbon, again valence 4, making 4 single bonds with 4 hydrogen atoms. And again, we can represent this with a dot structure. All of these electrons in the valence shell are being shared with hydrogen. We can use the line diagram. And again, this molecule is going to take what we call a tetrahedral shape as all of these pairs of electrons distribute themselves so they're as far away from each other as possible. Within this very sweet romantic relationship of sharing electrons and completing each other, sometimes these are not relationships of equals. So different atoms have different levels of attraction for those electrons, and this is known as electronegativity. So an electronegativity refers to an atom's ability to attract those electrons closer to it in a covalent bond. So the more electronegative an atom is, the more strongly it's going to pull those shared electrons toward itself. And the result of this is that different parts of this molecule are going to have different influences of these electrons. So oxygen is one of the most electronegative elements, and those electrons are going to be pulled more toward the oxygen. So in a water molecule, the side where the oxygen is going to have a higher negative charge just because those electrons are closer to that side. They're going to pull them away from these hydrogens. Because they're pulling hydrogen's electron away from it, the sides with the hydrogen are going to have a little bit of a positive charge. So we refer to this as a partial charge. So this Greek letter delta denotes this partial negative. So it's less than the full negative charge of a single electron because it's still being shared, but the oxygen's getting a little bit more of that negative charge from the electron. And similarly, on the hydrogen side, we would refer to a partial positive charge on the hydrogen, which would be less than the full positive charge of a single proton. So in a nonpolar covalent bond, the atoms share the electrons equally. So this is going to be more of an equal pull. Think of two people that are pretty much just as strong as the other pulling on a rope in a tug-of-war, and the rope's not going to go anywhere, right? In a polar covalent bond, one of the atoms in this bond is going to be more electronegative. The atoms are not going to share the electrons equally, and there's going to be this partial negative charge on the more electronegative atom. So we've gone over this. Unequal sharing of electrons causes that partial positive or negative charge for each atom or molecule. I mentioned earlier that when there is something that you need to commit to memory and just memorize rote, I would let you know this is one of those things. So you're going to need to know, at least among the most common elements in biology, the order of electronegativity. Hydrogen and carbon have very low electronegativity and very close to the same electronegativity. Oxygen is the very most electronegative, followed by nitrogen and phosphorus, which all have relatively high electronegativity. And the general trend across the periodic table is that as you go up and to the right, electronegativity increases. Being polar or nonpolar is going to have a huge effect on the properties of these molecules in biological systems. This is a very, very important characteristic of these molecules, as you'll see when we go on. So you need to understand that whether a covalent bond is polar depends on the difference in electronegativity between the two atoms, not on whether there's an electronegative atom present in this bond. So for example, hydrogen-carbon bonds are nonpolar because there's little difference between their electronegativities, not because there's no electronegative atom there. The converse of that is if you look at an oxygen molecule, so O double bonded to another O, it's also nonpolar because both of the two oxygen molecules are going to pull just as hard on those electrons, and they're going to end up sharing them equally. So because they both are having the same effect on those electrons, it's going to be a nonpolar bond. You get a polar bond when one of them is pulling harder on those electrons. So having these polar molecules causes another kind of interaction between molecules called a hydrogen bond. So a hydrogen bond forms when a hydrogen atom covalently bonded to an electronegative atom such as oxygen or nitrogen, and these partial charges are attracted to each other. So again, this is not going to be a strong covalent bond. This is going to be a relatively weak attraction. but the partial positive on this hydrogen, because the oxygen's pulling the electrons away, is going to be attracted to the partial negative charge on this nitrogen, which is pulling electrons away from these other hydrogens. So this is called a hydrogen bond. So in living cells, the electronegative partners are usually oxygen or nitrogen atoms, bonded either to hydrogen or carbon. So let's think about other kinds of compounds. So sometimes the difference in electronegativity between these two elements is so great that the more electronegative atom just steals the electron from the other one. It's just going to strip that electron away. So an example is the transfer of an electron from sodium to chlorine. So then once that electron has been stripped from the less electronegative element, now you have a situation where there's a charge on those atoms. So this is easier to see in this diagrammatic form. So here we have sodium with its single electron in its valence shell. Chlorine is just missing one, so chlorine is going to steal that electron. And so now sodium still has the same number of protons, but it's got one less electron, so it's going to have a positive charge. Chlorine also has the same number of protons, but now it has one extra electron, and this is going to give it a negative charge. So after the transfer of that electron, both atoms have an electrical charge, a net electrical charge to them, and a charged atom or molecule is called an ion. So this is a positive ion and a negative ion. So we call a positively charged ion a cation, and we call the negatively charged ion an anion. And the interaction between these two is due to opposite charges attracting each other. So these are going to get close to each other just because of the opposite charge. So we call this an ionic bond. And ionic bonds form compounds that are called ionic compounds or salts. But these are different from covalent bonds because this sodium doesn't become any less positively charged due to being close to this chloride ion. Now that it's an ion, we call it chloride instead of chlorine. It's still going to have this positive charge, which means that it can attract more chloride ions to it. And similarly, this chloride ion is no less negatively charged because it's attracted to and being close to this sodium ion, so it can also attract lots of other sodium ions to it. And so they tend to form these very densely packed crystals where each ion is going to be completely surrounded by the oppositely charged ions. This is what's known as a salt or a crystal. And now we come back to this very big idea in biology of structure and function. So we know that a molecule's size and shape are going to determine its function. A molecule's shape is going to be determined by the orbitals in the atom. So again, remember that these electron orbitals are getting as far away from each other as they possibly can. So we saw this earlier with the water molecules taking this kind of bent shape, as opposed to we saw earlier carbon dioxide is going to have the two oxygens on either side of the carbon because it's forming those double bonds. In this case, we've got two unpaired electrons taking up other positions, causing this one to have just a bent shape. So you can see this diagrammatically here. We've got the paired unshared electrons occupying those two orbitals. These are occupying the other ones, and it's going to have a particular shape because of that. And we also saw methane before that's going to have this specific tetrahedral shape as a result of those orbitals spacing themselves out evenly to be as far away from each other as possible. So in the book you read about S and P orbitals. S is just this closest orbital, the nearest shell. The P ones are the four outer orbitals, and these are going to create the shapes that the molecules take. So there can be strong and weak chemical interactions. So we saw that covalent bonds are relatively strong bonds. So these are going to form the structure of the molecules in terms of what's the order of atoms in, say, like a long chain molecule. Those are going to be the covalent bonds that determine that structure of the molecule. But it's also possible for these large biological molecules to have these weak interactions between different parts of that, say for example, a long chain. And so they're going to be held into this specific shape, a functional form, by these weak interactions such as hydrogen bonds. And so these weak bonds are highly reversible. These bonds can form and break, and that's going to give these biological molecules a lot of flexibility in the different configurations that they can take. So this can be a big advantage in terms of the flexibility of function in these molecules. So an example is this very, very complicated protein structure that if you follow this kind of thread, this is sort of the primary structure of the sequence of amino acids in this very complicated molecule. But within this string, there's all of this folding and coiling and all of this higher layers of shape to this. And these are all formed by these weak interactions that help determine the shape. And the shape is going to, of course, determine the function. So molecular shape determines how biological molecules recognize and respond to one another. So we'll see a lot of situations where there are receptors for a protein that respond to the shape of that protein that can only bond if it has the right shape. And this is sort of a lock and key mechanism that allows these chemical reactions to occur. And so an example of this specificity of the shape of these molecules is the case of opiates such as morphine. They mimic the shape of the active portion of a natural endorphin that your body normally produces to help to control pain and stress levels. And so their region that interacts with these receptors are close enough in shape that either of these, either the natural endorphin or the morphine, can bond to these receptors and produce the same effect of helping with pain and lowering stress levels. So the next major concept in the book is chemical reactions. So what are chemical reactions? They're basically making and breaking chemical bonds. So in chemical reactions, we usually think of the starting molecules as being the reactants. So we usually put those on the left-hand side of a chemical equation. And then after they react together, they break bonds, they rearrange their atoms to form products. And we put those products on the right-hand side of this reaction equation. So here we have two hydrogen molecules, a single oxygen molecule. They're going to undergo some kind of reaction where bonds will be broken, they'll be rearranged to form two water molecules. So a very important chemical reaction that we're going to be learning a lot about is photosynthesis, and this is where sunlight provides the energy to convert carbon dioxide and water to glucose and molecular oxygen. So what we can notice about this is that although these atoms, the bonds between them are broken and the atoms are rearranged, the atoms themselves do not change. You have the same number of atoms going in as you have coming out, and we can easily convince ourselves of that by just counting heads. So on the reactant side, we have 6 carbons here, so 6 molecules of carbon dioxide have 6 carbon atoms. The number of hydrogen atoms is going to be, so 2 hydrogen atoms per water molecule times 6 water molecules is going to be 12. And then oxygen, we've got 2 oxygen atoms per carbon dioxide, 6 carbon dioxides for a total of 12 there, and then 6 more in the water for a total of 18. If we look at the product side, we still have 6 carbon atoms, 12 hydrogen atoms, 6 oxygen here, plus another 12 over here to give you 18. So these chemical reactions just rearrange the atoms. They do not change the atoms in any way. They can't create or eliminate any atoms. It's just going to shuffle them into a different form. And we should note that all chemical reactions are reversible. So the products of what we would call the forward reaction, although because they're reversible, what you call the forward reaction versus the reverse reaction is a little bit arbitrary. But if we think of the products of the forward reaction, they become the reactants for the reverse reaction. So in this case, with molecular hydrogen combining with molecular nitrogen to form NH3 or ammonia, it's also possible for this ammonia to dissociate again back into hydrogen and nitrogen gas. And we usually assign the reactants and products according to which way the majority of the reaction will go. And so ammonia has a lower energy state, lower potential energy than hydrogen and nitrogen gas. So primarily this reaction is going to go in this direction. But this reaction is going to release energy. That energy is going to cause some of this ammonia to dissociate back into the molecular gas form. So how do we know what the balance of this reaction is going to be? So we know that there's going to be a forward reaction occurring all the time with a reverse reaction occurring at some rate. And we say chemical equilibrium is reached when the forward and reverse reactions occur at the same rate. So every time we've got a hydrogen and nitrogen molecule combining to create ammonia, we also have an ammonia turning back into hydrogen and nitrogen. They're going to occur at the same rate. That doesn't necessarily mean they're in equal quantities, right? If the reaction is primarily going in this direction, it's possible that there will be just a tiny amount of the hydrogen and nitrogen gas and mostly ammonia, but the rates of reaction are occurring with equal frequency. So at equilibrium, the relative concentrations of reactants and products do not change. So again, you can have mostly ammonia and just a little bit, but they're not changing even though the reaction is still proceeding in both directions. This is a very important concept to understand, that they're not going to be equal concentrations of the two. They could be very different concentrations of reactants versus the concentration of products. But the rate of reaction from reactants to products is going to be the same rate as the reaction of products going back to reactants. Okay. If you're struggling with this idea a little bit, spend a little time with the book. It's a tricky one. So one of the definitions of life that you heard about, hopefully you watched that What is Life video that I recommended for the first day of class. Austrian physicist Schrödinger defined life as that which resists decaying to disorder and equilibrium. What does it mean to resist equilibrium? How do you keep equilibrium from happening? So the way you do that is to keep adding more of the reactants and keep removing the products. You've got a steady supply of large amounts of reactants and small amounts of products. It's going to keep that reaction moving in the forward direction and keep it from reaching equilibrium. This is one of those special conditions I told you about where life is obeying the same rules as anything else in chemistry, but it has some tricks to keep things from reaching equilibrium, to keep things from settling down, keep them from doing things that non-living things do. So in conclusion, we started this out by talking about the different kinds of explanations that you'll be hearing as we go along for how different things work. And so we definitely talked about differing charges being attracted to each other. This is going to be incredibly important in many, many biological processes, with ions moving along a concentration gradient or along an electrochemical gradient due to that attraction to its opposite charge. When we say that molecule X has a natural affinity for molecule Y, what we're really saying is that molecule X and molecule Y are going to be in a more stable, lower energy state when they're together than they will be when they're apart. So whether it's atoms coming together to form molecules and they're going to be more stable when they share those electrons, or partial charges on different molecules coming together because of their opposing charges, different shapes fitting together, those natural affinities are going to come due to lower energy states and higher stability when they're together as compared to when they're far away from each other. And then we also talked about weak interactions between molecules, and when we think about things binding reversibly to their receptors, they're going to bind. That binding might cause both of the molecules to change their shape. That change of shape might cause them to lose that interaction. And so this is due to those weak intermolecular forces that we were talking about. So now we're ready for the next step to think about why water has the properties that it does and why it is the fundamental, most important substance for life being able to exist.